In the upper left, you see there was no ozone hole back in 1979. It actually looked much more like the northern hemisphere now, where you have this ring of high ozone, the red and white values there around the pole. And it's only as you move into the 80s that you start to see blue and purple colors show up, and they get more and more intense. And I think our record ozone hole was about 86 Dobson units. Yeah. How small did it get? About 86 Dobson units in 2006. It was the record low. So this series, NASA put this series together to show folks the ozone hole didn't always exist. We've been watching it by satellite since 1979. You can see it really developed in the 80s. They've been launching balloons at the South Pole since the International Geophysical Year in 1958. These are 3 profiles on 3 different dates. The blue one is September 2nd, so the sun hasn't come up on the pole yet. It's still dark. And hey, it looks a lot like our ozone profiles, right? You see there's some ozone in the troposphere, about 10 kilometers you hit the tropopause, and the ozone goes up dramatically. And if you integrate that, you get 282 Dobson units of ozone, which is a little lower than what we see here, but not by much. However, you go to October 5th, that's the red curve, and October 8th, the green curve, and notice what happens in the altitude range where ozone on September 2nd was most plentiful. It's gone. There's no ozone left, right? You see altitudes there where it's reading 0. That's how this got the name ozone hole. There really was no ozone at those altitude levels. And when the ozone hole forms, you get right where the ozone is most plentiful, ozone's completely depleted. And that was seen in the balloon data. NASA actually, this is one of the sad stories for NASA. So they were looking at satellite data. They saw the ozone hole in the satellite data, but their data software processing algorithms rejected the data because it was below the range that was expected to be observed. So they had known about the low ozone values in the pole before the first paper got published on the ozone hole, but they discounted, they didn't believe their satellite observations. And satellite atmospheric observations were still developing, and so people weren't quite as confident as they are today in the satellite observations. So ozone hole develops in August, fully developed by October, broken up in early December. So it's not around all year round. It's only there from August to October. First began to appear in the 80s compared to the 70s. The 90s were 60% lower. We ended up probably 75% lower in its worst years. 100% ozone loss between 12 and 20 kilometers over Antarctica, right where it normally is most plentiful. I'll show you a graph in a minute of the size of the ozone hole as a function of time. And that meteorology is important to the development of the ozone hole. So this was the paper by Dobson. He observed in 1966 the black curve there at Resolute, and that's a northern hemisphere station, and then the blue curve at Halley Bay, which is Antarctic station. And you can see that back in the 60s, there were differences in the behavior annual cycle of ozone over these 2 sites. Resolute showed a big peak in March, and an annual cycle with a minimum in August, September. The southern hemisphere, Antarctica, was behaving differently, but you see the minimum sort of May through September, not much going on, and in fact, in November and December, a peak in the ozone. Then you go to 1994, and this was not obviously in Dobson's paper in 1966, but look at how differently the Halley Bay ozone looked in 1994 as compared to 1966. Instead of ramping up in October and November, it dropped off the table down to almost 100 Dobson units. This was a real puzzle. And so the first papers hypothesizing catastrophic ozone losses in the stratosphere from chlorine molecules came out in about 1972. Mario Molina and Paul Crutzen ended up winning the Nobel Prize for this work. There was a colleague of mine at NASA Goddard who was also instrumental in identifying the chlorine chemistry, but his name was kind of fourth in line. The Nobel Prize usually only goes to 3. So he was invited to attend, but he had to watch his colleagues get the Nobel Prize, and he did not. He's a very generous spirit and a wonderful colleague. But there was a lot of debate while they were trying to figure out what was going on, because if you went to models and you knew gas phase chemistry, you could not get 100% ozone loss at 20 kilometers in the gas phases. It didn't work. My advisor at NASA, Mark Schoberl, was a big proponent of dynamical influences on ozone, that the meteorology and the strong descent in the polar Antarctic stratosphere, stratosphere was responsible for the low ozone concentrations we're seeing. Susan Solomon hypothesized it was about chemistry. The key to the chemistry was the development of these pretty high altitude clouds. It's dry here in El Paso, but it's really, really dry in the stratosphere. There's almost no water in the stratosphere. How do you form clouds in the stratosphere? It has to be really, really, really cold. And there's really only one place on the planet that is cold enough to form clouds in the stratosphere that persist. And that's Antarctica, because back at the beginning, you remember we had this isolated air mass that gets no sunlight for months. And so it just radiatively cools the space. It gets so cold that water in the stratosphere can freeze. Nitric acid trihydrate also freezes. And these crystals allow for heterogeneous reactions to occur of the chlorine species that do not occur in the gas phase. That was the key to understanding the ozone hole. So the ozone hole develops because of heterogeneous chemistry on clouds in the stratosphere. That's pretty cool. Some aircraft data shows you what happens when you fly into the ozone hole. On the left, before the sun comes up. On the right, as the sun is coming up, they're measuring two things here: chlorine monoxide, which is the yellow curve, and ozone, which is the red curve. And you see as you fly into the polar vortex in August, ozone is kind of flat, but there's chlorine monoxide present, and we know the CLO is there. As soon as the sun comes up, the ozone goes down right where the chlorine is. This was kind of a smoking gun plot to link the chlorine to the ozone losses. But how in the world does chlorine get up there? CFCs are heavy molecules. Why are they in the stratosphere anyway? And that has to do with the large-scale circulation of the atmosphere. So this stuff gets lofted in the tropics with strong convection. Some of it makes it into the stratosphere. Stuff that gets into the stratosphere stays for a long time, 30 years, 50 years. So the CFCs we started putting up in the atmosphere back in the 1940s, 30, 50 years later, they're coming down, and we ramped up CFC production in the 70s. CFCs were everywhere. So we were injecting a lot of CFCs in the atmosphere. And you can kind of see in this plot, this is a satellite image of CFC-12. You see in the tropics, the high values rising up higher into the atmosphere, and then they're descending into the polar region. So CFCs did make it into the stratosphere. Now, the international community came together in a rather laudable way back in the 80s. Before the science was completely understood, in 1987, the Montreal Protocol was signed, or an international agreement to reduce and eventually eliminate CFCs. There was an amendment in 1992, I believe in Copenhagen, that accelerated the timeline for the retirement of CFCs. And you can see the CFCs present in the atmosphere have been decreasing since about 1994. So the international community did come together to curtail the emission of CFCs into the atmosphere. It's a really beautiful story because while the science was being uncovered, the politicians, the business leaders were coming together and agreeing upon a solution. Ozone hole area. There's a lot of lines on here. The dashed line is the mean of the area from August to December. The little dotted line in the middle shows you how big the ozone hole gets in millions of square kilometers on average over that 10-year period. The green curve was the 2014 hole, which kind of went along the average line. The blue curve was the 2015 hole, which was actually really, really big. One of the biggest ozone holes we've seen. And then 2016, the red one, we're kind of back smaller than the mean. So there are hopeful signs of recovery in the ozone hole. We're still not there yet. CFCs are still present in the atmosphere. Take a long time to come out of the atmosphere, but encouraging news. And this just shows you, this is a month on the horizontal axis, total column ozone on the vertical axis, and you can see the mean over the 1979 to 2016 period, with the minimum occurring in late September, early October. I think I'm going to skip some of that. Here's what the models suggest are going to happen. This is an old slide, but had we not done anything to curtail CFCs, the total chlorine in the atmosphere would have gone along the red curve. The London amendments and the Copenhagen amendments kept reducing that timeline. We're kind of, last conference I went to where I saw talks on this, they're kind of expecting by 2050 that we'll be back to 1980. So in your lifetimes, the ozone hole will heal. That's good news. That's a good story. That's my quick overview of stratospheric ozone. Any questions about that one? Because I'm going to talk about tropospheric ozone in a second. Yeah.
What are some of the